Hi, I'm Chris, and today I'm going to be explaining AC circuits. What are they, and everything you need to know about them in a physics class. By the end of this video, you will know what an AC circuit is, what RMS voltages and currents are, reactance, capacitive and inductive, impedance, phasors, and power factor. So let's begin with our first question. What is an AC circuit? A DC circuit is an electric circuit where the source delivers a constant voltage. An AC circuit is an electric circuit where the source delivers a variable voltage. Current is induced in a wire when the magnetic flux through the wire changes. If the wire is rotating with an angular velocity omega, there's going to be an induced voltage given by this equation right here. And we can simplify it to say the maximum voltage times the cosine of angular frequency times time. Over on the right, I've drawn a graph which shows how the voltage changes over time. It is a cosine wave going from positive maximum voltage to negative maximum voltage and back. This leads to a concept called RMS, which means root mean square. So if you look at this graph, you can see the voltage is changing over time. And sometimes we might want to know what the average voltage is. The problem is, if you take the average of a cosine, you get 0, because every portion above the line gets countered by a portion below the line. To get around this, we take the average of the absolute value, or rather, we square it, then we take the mean, then we take the root of the mean of the square. So VRMS is calculated by taking the square root of the mean of the square. The bar means mean average. And with a sine and cosine, this comes out to the maximum voltage times the square root of 2. The same thing applies to the current. The current will also follow a sine or cosine, which means there's also an RMS value of the current. Why is this useful? Why do we care about RMS averages? Well, one reason is because it tells us the power consumed by a resistor in the circuit. And any appliance, for instance, that you plug into the outlet in a wall can be thought of as effectively a resistor. So the equation would be the average power is equal to the voltage RMS times the current RMS. Now, it is very important to note that this is not the power delivered by the source. It is the power consumed by the appliance or by the resistor. This is an important distinction because the power delivered by the source has a slightly different equation, which we'll get to later. Moving on, we're now looking at a new concept called reactance. So in a DC circuit, a resistor has resistance. In an AC circuit, because the voltage is varying with time, inductors and capacitors also have effective resistances called reactances. So here you can see the three main components of an RLC circuit. We have the inductor. It resists a change in the current. Its symbol is L, and its unit is henries. The resistor, you probably know from DC circuits, it resists the current. Symbol is R, unit of ohms. A capacitor follows a change in current. You remember from a DC circuit, when the switch is closed or opened, a capacitor will charge or discharge. In an AC circuit, the voltage across a capacitor follows the current. Its symbol is C, and its unit is the farad. In DC circuits, inductors and capacitors have 0 resistance. In an AC circuit, inductors and capacitors have an effective resistance called reactance. So here is a graph of the current over time. The current, like the voltage, has an equation, maximum current times the cosine of angular frequency times time. You might think, what is this angular frequency here? Angular frequency is frequency, cycles per second, but in units of radians. So the equation for angular frequency is 2 pi times the frequency. So if you look at this graph, this cosine graph, a cosine is the adjacent side of a triangle. So if we look over on the right over here, we've got a triangle and its hypotenuse is the maximum current. So the actual current is down here. It is the adjacent side of this triangle. And over time, this maximum current, this hypotenuse vector, it stays at a constant length, but it rotates around the circle counterclockwise. And as this maximum current vector rotates around the circle, the cosine goes between negative I maximum and positive I maximum. This type of vector that rotates around a circle with time is called a phasor. And no, it has nothing to do with the Star Trek energy weapon. We move down, we find that we can write voltages, we can draw voltages on the same type of diagram. And when we do, we get the voltage across the resistor points in the same direction as the current, which you know from V equals current times resistance. The voltage across the inductor leads the current by pi radians, or 90 degrees. And the voltage across the capacitor lags the current by pi radians, or 90 degrees. So on this phasor diagram, the inductor voltage and the capacitor voltage point in opposite directions, and they're both 90 degrees from the resistor voltage. That means when the resistor has maximum voltage, the inductor and capacitor have 0 voltage, and when the inductor and capacitor have maximum voltage, the resistor has 0 voltage. If we want to write equations for the horizontal components of each of these vectors, for the resistor, it equals maximum voltage times cosine omega t. For the inductor, it equals maximum voltage times negative the sine of omega t. And the reason it's negative is because if you look at this vector over here, the angle that matches with this angle goes with the other axis, which means the sine goes this way. And that is a leftward pointing arrow, which means that's a negative number, but the sine of the angle is positive. So that's why there's this minus sign here in the inductor voltage equation. And for the capacitor, it is the maximum voltage across the capacitor times the sine of omega t. And that gives us this component over here, which, as you can see, is positive when the vector is pointing to the right, which means it is indeed positive when the sign is positive. Continuing on, if the voltage across the resistor is equal to the current times the resistance, and I'm actually going to rearrange this because I want to explain it a different way than I did when I set this up. So we can also talk about the voltage across the inductor and the voltage across the capacitor. I want to make sure you can see that diagram, my bad. So the voltage across the inductor would be equal to the maximum current times what's called the inductive reactance, and the voltage across the capacitor is equal to the current. I should say this is max current times the capacitive reactance. And I believe this only works for maximum current, not actual current, because the voltage across the inductor and capacitor are maximum when the current is 0. So these equations only work with maximum current. All right, so we've introduced these new variables, these new concepts called reactance. So what are they? How can we calculate them? So here are the formulas. The inductive reactance is equal to the angular frequency times the inductance, and the capacitive reactance is equal to 1 over the angular frequency times the capacitance. And again, this is the angular frequency supplied by the voltage source. All right, now that we've gotten through these phasor diagrams, we can now talk about impedance, which is like the equivalent resistance of the entire circuit, including inductors and capacitors. So over here on the left, we have another phasor diagram. And as you can see, I have plotted not voltages, but resistance and reactance. And we can do that because if you look at these equations, these voltage equations, just divide each voltage by the current, and you get the resistance and the reactance. So that's why we can plot the reactances on a phasor diagram. And again, these are going to be traveling around in a circle. Impedance is the effective resistance of the circuit. That's what we get when we add the vectors together of the resistance and the reactances. So if you take this arrow, the reactance for the capacitor, and move it up to the end of the inductor reactance, we're subtracting the reactance of the capacitor from the inductive reactance. And then we're adding the result with the resistance to get a new vector that points from the origin to the edge of the rectangle that the resistance and the reactances make. So adding vectors should be familiar from Physics 1 and from earlier in Physics 2. Because of that, we can write the impedance as the Pythagorean theorem. Z squared is equal to the resistance squared plus inductive reactance minus capacitive reactance squared. And this here, the impedance, is the effective resistance of the circuit. So for the voltage of the circuit as a whole, we can write V, this is the voltage supplied by the source, is equal to current maximum, it has to be the maximum voltage, equal to current maximum times impedance. And this also works with RMS values. The average power supplied by the source is equal to V RMS times I RMS. But again, remember last time we talked about power, it was the power used by an appliance or a resistor. This is the power supplied by the source, so it's slightly different. We have to multiply by the cosine of an angle. And this angle is the angle here between the impedance and the current. This angle is called the power factor. Another way of writing the power, which you might see in a textbook, is maximum voltage times maximum current over 2 times 1 over square root for both RMS voltage and current times the power factor, cosine V. It's very important to remember that power factor is not a measure of power. It is a number that you multiply by the general equation for power in an AC circuit to get the actual power. Cosine V is called the power factor, and we can find it because, remember, we're looking at triangles. It is the adjacent side of the triangle divided by the hypotenuse. So the power factor is equal to the resistance divided by the impedance. And if we scroll up to look at our voltage diagram, it would end up being the resistance voltage divided by the total voltage. VR max divided by V supplied max. That's the basics of AC circuits. We covered what an AC circuit is, how an alternating current is created. We talked about what RMS is. It's the average of the square of the voltage and the current. And RMS voltage and current are useful when calculating the average power consumed by a resistor or an appliance. Lastly, we talked about the AC equivalent of resistance that is found in inductors and capacitors, which is called reactance. We looked at a graph on a current and plotted it as a phasor vector, which rotates around a circle, with the actual current being the horizontal component. We then plotted the voltages of a resistor, inductor, and capacitor on a phasor diagram. The inductor voltage leads the current by 90 degrees. The capacitor voltage lags the current by 90 degrees. We found equations for the maximum voltage across the resistor, inductor, and capacitor, and learned a new concept called reactance, which is the inductors and capacitors version of resistance. Finally, we put all of them together on a graph in a vector sum, which we call the impedance. We get the impedance by taking the Pythagorean theorem with the resistance and reactances. It tells us the relationship between the supplied voltage and current, and the average power supplied by the source can be calculated using the power factor. That is the cosine of the angle between the impedance and the current. That's it for today. Thanks for watching. If you have questions, let me know in the comments. If you would like to contact me for tutoring, visit my website in the description. And if you'd like more free physics explanations like this, you can subscribe to the channel. Thanks again for watching. Happy studying.